Hi everybody. For this video we're going to be taking a look at the converse of the Pythagorean theorem. Now we know that the converse of an if-then statement is where you take the conclusion and you put it where the hypothesis was, and you take the hypothesis and put it where the conclusion was. So since we already know what the Pythagorean theorem says, we should be able to make a pretty good guess about what the converse of the Pythagorean theorem says. But just to remind ourselves, the Pythagorean theorem is usually it's just thought of as a squared plus b squared equals c squared. But the longer version of the Pythagorean theorem says that if you're looking at a right triangle, then the square of the hypotenuse is equal to the sum of the squares of the legs, and that square of the hypotenuse equals sum of the square of the legs. That is usually just kind of translated into c squared equals a squared plus b squared. So there we have our if-then statement that we're going to be looking at the converse of. So you can guess we are going to be taking this part and putting it up in the front, and we'll be taking this part and putting it in the back. So let's jump right in and take a look at Theorem 8-3 here. It would say that if the square of one side of a triangle is equal to the sum of the squares of the other two sides, then the triangle is a right triangle. Or, in other words, if we had this diagram here, and if we knew that c squared is equal to a squared plus b squared, then we would know that triangle ABC must be a right triangle. And furthermore, we would know that since c squared is what the other two legs squared add up to, and here's c right here, that would mean that c would be the hypotenuse of the right triangle, and so our right angle would be across from c right there. And so that's the converse of the Pythagorean theorem. It's just stating that if you can set up this arrangement of c squared equaling a squared plus b squared, it tells you that the triangle you are looking at must be a right triangle. Now there's a little concept here that you might want to be aware of. It's this idea of Pythagorean triples. And a Pythagorean triple is when a trio of whole numbers works in the Pythagorean theorem. So we call those Pythagorean triples. It's a trio of whole numbers that will satisfy the a squared plus b squared equaling c squared. There are technically an infinite number of these, but there are a few that are kind of the basic Pythagorean triples that use, the smaller of the smaller numbers. Some of the Pythagorean triples get really, really big. But the smaller numbers that fit into the Pythagorean theorem, or the smaller Pythagorean triples, are some things that you might want to be aware of. And we can see there are 4 of them right down here. 3, 4, and 5 is probably the most well-known Pythagorean triple because 3 squared plus 4 squared equals 5 squared. 3 squared, we got 3 squared, which is 9, plus 4 squared, which is 16. 9 plus 16 equals 25, which is what 5 squared is. So 3, 4, 5, that's probably the most famous of the Pythagorean triples. But there are others. 5, 12, and 13 works because 5 squared plus 12 squared does equal 13 squared. It's 125 plus 144, which equals 13 squared, which is 169. 8, 15, and 17 work because 8 squared plus 15 squared equals 17 squared. And 7, 24, and 25 is a Pythagorean triple because, and you can check it on a calculator if you want, but 7 squared plus 24 squared equals 25 squared. And like I said, there are an infinite number of other Pythagorean triples, but these are the 3 kind of the 3 that use the smallest of the smallest numbers. And it might be a good idea, like I put down here, it might be helpful for you to memorize this first row right here. But what are these other spaces for? Well, you can actually create new Pythagorean triples pretty easily. You can create new Pythagorean triples by simply multiplying each number that's in an existing triple by a whole number. Technically a non-zero or technically a positive whole number is what you'd be looking for here, but I'll just say a whole number. So in other words, we can take 3, 4, and 5 and we can multiply each one of those by 2, and you would have 6, 8, and 10. And that's a Pythagorean triple. 6 squared plus 8 squared equals 10 squared. Or you could multiply each one of those by 3, and you can get 9, 12, and 15. And that's a Pythagorean triple. Or you can multiply them by 10, and you could have 30, 40, and 50. And that would be a Pythagorean triple. And again, the helpfulness there is that if you're working on a problem where you're using a Pythagorean theorem, if you can notice that two of your sides are 3 and 4, let's say, then without doing the actual work, you can just realize that the third one would be 5. Or if you notice that you have a hypotenuse of 15 and one leg that's 12, then if you've kind of got this idea of 3, 4, 5 triangles, and you notice that there you got a hypotenuse of 15 and a leg of 12, then the other leg must be 9. And so that can be kind of helpful. And you can maybe fill out the rest of this chart if you want, maybe doubling all these three numbers. And so you have 10, 24, and 26 as another Pythagorean triple. We're multiplying these all by 2, and 16, 30, and 34 would be another Pythagorean triple. And so you can kind of fill out some of these other spots, but really it's that first row that's kind of the key there. If you know 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25, it could actually save you some work when you're working on some of these Pythagorean theorem problems. Now there are a couple other things that we're going to take a look at that are related to the converse of the Pythagorean theorem. Theorem 8-4 and 8-5. And Theorem 8-4 says that if the square of the longest side of a triangle is less than the square, or the sum of the squares of the other two sides, then that actually tells you that the triangle would be an acute triangle. So in other words, in this picture right here, where we have triangle ABC with sides of A, B, and C, if I picked out the longest of the sides, which we'll say is C, if C squared is less than A squared plus B squared, then triangle ABC has to be an acute triangle. So in other words, you can decide that this is an acute triangle without actually knowing any of the angle measurements. If you know all three of the side lengths, you can take the longest one and put it as C, square it, compare it to the other two sides squared and added together, and if the other two sides squared and added together are bigger than what the longest side squared is equal to, then you know you're looking at an acute triangle. And we'll do an example here in just a second when we get down to example 1. But first, let's look at Theorem 8-5, which is related, and it's looking at, well, what happens if C squared is bigger? So what it says is, if the square of the longest side of a triangle is greater than the sum of the squares of the other two sides, then the triangle is obtuse. So in other words, in a picture like this, where we have longest side of C and the other two sides are A and B, if we take C squared and it ends up being bigger than A squared plus B squared, then triangle ABC here would have to be an obtuse triangle. So in other words, what we now know is that if C squared equals A squared plus B squared, then that's a right triangle. If C squared is smaller than A squared plus B squared, that's an acute triangle. And I think of it as when A squared plus B squared is bigger, it's acute. Right, so the A's kind of go together. A squared plus B squared being bigger, acute. And lastly, we know that when C squared is bigger than A squared plus B squared, that's when we're looking at an obtuse triangle. So let's do just a few examples real quick where we can apply those three potential cases and decide whether we're looking at acute triangles, right triangles, or obtuse triangles. So on example A down here, we know we have 20, 21, and 29 as our side lengths. We don't even have a picture to look at, but with just those side lengths, we can just decide whether it's going to be a right triangle, an acute triangle, or an obtuse triangle. Now, the C in our C squared, A squared, B squared arrangement has to be the longest side. So 29 is going to be our C. So 29 squared is what we're going to compare to the other two sides added together. It doesn't matter which one's A and which one's B, but the longest side always has to be C. So we're going to compare 29 squared to 20 squared plus 21 squared. Now 29 squared is going to give us 841. 20 squared plus 21 squared, well, 20 squared is 400, and 21 squared is 441. So 21 squared plus 20 squared is 400 plus 441, which that is going to give us 841. So we're looking at 841 equaling 841. So that means that this right here has to be a right triangle. It also means we found another Pythagorean triple. 20, 21, and 29 is a Pythagorean triple. But because the C squared equals the A squared plus B squared, that makes that a right triangle. Now in example B, we got 20 and 21 as our A and our B, but now our C is going to be 30. So we're going to be looking at 30 squared compared to 20 squared plus 21 squared. Now we know this is still going to be 841. That's not going to change. And 30 squared is going to give us 900. So in this case, the C squared is bigger than the A squared plus B squared. So that's this case right here, which means we are looking at an obtuse triangle. And down here, we have 20 and 21 again as our A and our B, and now our C is going to be 28. So we're looking at 28 squared compared to A squared plus B squared, which will be 20 squared and 21 squared. So again, 20 squared and 21 squared is still going to be 841. And now 28 squared is going to be 784. So in this case, the A squared plus B squared is bigger. So this is an acute triangle. So you can see we've gotten one of each. Now if you want, you can pause right now and try 5, 6, and 8 and see whether that's acute, right, or obtuse. So if you want to hit pause right now, you can try that. Okay, now let's take a look at this. 5, 6, and 8. The biggest one is 8, so that's got to be our C. The other two can be A and B. So we're going to compare 8 squared to 5 squared plus 6 squared. Now we know 8 squared is going to be 64, 5 squared will be 25, and 6 squared will be 36. If I add 25 and 36, that's going to give me 61. So now I have 64 compared to 61. The 64 is bigger, so that means my C squared was bigger. So again, I am looking right here at an obtuse triangle. So there you have it. That's an application of the converse of the Pythagorean theorem. We can take the three sides of a triangle, arrange them in our C squared and our A squared plus B squared, and decide whether it's a right, an acute, or an obtuse triangle based on whether the C squared equals the A squared plus B squared, or the C squared is smaller than the A squared plus B squared, or the C squared is bigger than the A squared plus B squared. All right, we will see you in the next video.